Hello, it's Keith here, and this is lesson 14 of the Chibiakumas series of my Z80 programming tutorials. Now, we've been looking over the last few weeks at how the player driver works and how the player is drawn on the screen, but I want to move on from that to something that I think you might find quite interesting. I want to discuss how the background is drawn in the game. Now, the background, of course, is a parallax scrolling simulation, so it looks like parallax, but it technically isn't. Of course, the important thing with the background is it has to be very, very fast. Essentially, the game is a bullet hell shooter on an 8-bit system, which is a challenge enough. The game has up to 255 bullets on the screen at a time and up to 63 sprites on the screen at a time. This means there's very little processing power left, and because it's a software scroll, we have to redraw the background every single frame, and there's really no processing power left to do this, so we have to effectively draw the background in a comparable amount of time as it would take just to clear the screen. On the CPC and the Enterprise, the screen is 16 kilobytes of memory, so it's quite a big amount of data we have to push, so we're really having to do things very, very quickly. And because of that, the way I draw the screen in Chibiakumas is there's a piece of code which is solely designed to draw the screen, and it uses various plugin modules that will do different areas of the screen in different ways, and that's how we get the speed as fast as we possibly can. During early testing in Chibiakumas episode 2, I did have a piece of test code that would have allowed for a full tile map with various different tiles, but it was far, far too slow. The game would have been massively slower, so I ditched it, and instead we end up with these simple tiles which are a repeating 8-byte wide tile, and this gives a width of 32 pixels on the Amstrad CPC or 64 on the ZX Spectrum, because the ZX Spectrum is 1 bit per pixel and the CPC is 2 bits per pixel. And so now I want to have a look at a sample screen which we've got here, and I am also going to have a look at the source code, and we're going to very quickly compare the modules of the source code with the areas of the screen, and then we're going to look at them in more detail so we see exactly how they work. I know the screen's very small here, but we're just going to very quickly discuss the areas. We're going to look at the code separately. So essentially this screen is drawn in separate sections, and each section is drawn by a specialised piece of code that solely draws that kind of area. So you have a gradient at the top here. You then have a tile map here, which is this repeating tile. Then you have a blank area, which is flood filled. Then you have a tile map here, which is these scrolling buildings here. Then you have a blank area here. Then you have a gradient here. And then you have another tile map here. And the point I'm making here is that if we got our gradient code to draw our filled area, that would be significantly slower. And again, if we use the tile map area to fill this with just a blank tile, it would be very, very slow. So the idea is we do everything with the simplest code that can do the job. So the gradients code is slightly easier than the tile code, which is much more complex than the blank area code. So it's using each piece of code to fill each area as fast as possible. And the net result is hopefully that the background is drawn with relatively little time used. So let's have a look at how the drawing works. Now, the MSX uses a different version to the CPC and the Spectrum, but the CPC, Spectrum and Enterprise basically use the same code. The code is executed with the HL pointer pointing to the far right hand side of the top line of the screen. The screen's drawn down consecutively, and it does it from right to left because it's mostly using stack misuse. This is where we use the stack, and we do lots of push commands to fill very quickly. And we're going to see that later. So the first area here, this red area, is done by this code here, which draws a gradient. Then this area here is drawn by this area here, which draws a tile map for the clouds. Then we have a blank area, which is drawn by this area here, and that's this area. Then we have another tile map, this cyan area here, which you can see here. Then we have another blank area, this magenta area here. Then we have this yellow area, another gradient, and this is the bottom of the screen here. And then we have this orange area here, and this draws this area here. Now, once the drawing is complete, we do have to handle the scrolling of the tile maps. The gradients scroll automatically, the blank areas don't scroll at all, but the tile maps do need to be scrolled separately, and we are going to look at that as well later on. So in today's episode, I'm going to go over the very basic code that calls each of these subroutines, the tile, gradient and solid fill routines, and then next time we're going to look at the solid fill and the tile map, and then finally in another episode we'll look at the gradients because they're quite large. So today we're just going to have a quick look at the overview of the code, and we'll see how these separate modules are called. So first of all, we have some code relating to the MSX. The MSX version is totally different. It may look the same, but it's very different, and that's because the MSX screen is very different. So that's the reason for that difference there. We're going to have a look at that later on. So here is the start of the Spectrum code. And you can see, first of all, we've got this gradient execution code here, which will draw the gradient. And that we're drawing this top one up here. So the important thing to notice is HL will be the top right of the screen when this is called, the memory address that is. So we are loading DE with a pointer to the gradient data. Now here's the gradient data just here. The first 2 bytes are the byte pattern of the top line of the gradient. You see the gradient alternates between 2 bytes every pair of lines. And so we need to initialize it with 2 bytes for the first line that's drawn. And then we can set offsets and add another byte, which will push one of the bytes off, and then it will alternate between these 2, and then alternate between these 2, and then these 2, and so on until we get to the end. And the end is marked by 255. The screen's only 200 pixels tall, so there can't be a line 255. So that's our gradient pattern here, and that's the colors that we need to draw these. These are, of course, in byte format, in this correct format for the screen. Now, the Spectrum version is almost identical, obviously a different bitmap pattern, but the code is basically the same. So here we've got the address for the byte pattern for the gradient. Here we've got the number of lines. We're going to draw 48 lines here to draw this top part. Here we've got a bit mask, and this is relating to the scrolling. Now, the parallax scroll occurs by scrolling different parts of the screen at different speeds. So the bottom of the screen scrolls fast. The top of the screen is supposed to be in the distance, so it scrolls slowly. You can see here that these 2 bits are 0, and this is slowing the scrolling effect because this is ANDed with the ticks occurred, and so this is quite slow. If we put another 0 in here, it would be even slower, and if we change it to a 1 here, it would be even faster. So that's what this does. And then we're calling out to this command, which does the background gradient, and this is part of the core. So that's the first top gradient handled, and so now we need to do these clouds. So the first thing we need to do is we need to get the memory address of the cloud data. Now here's the tile map data. It's loaded in as a sprite into the level data itself, and so you can see if we just scroll through these, each one is 32 pixels wide. They have to be. That's 4 pairs of 2 bytes. There's a good reason for that we'll go into in a later lesson. So you can see here that these are the byte data, and there's some extra ones for the vertical levels and so on and so forth. So we are having to find the address that this actually occurs in memory, and what we do is we use this get_sprite_mempos command with the address of the start of the tiles and the offset as a sprite number, and these sprites have a header that will allow us to get the memory address. Now it's important to notice that for the quad sprite, which is the tile code that handles the clouds and things like that, the data does have to be aligned to a 256 byte origin, otherwise it will start to malfunction in some cases, so you do need to be a little bit careful with it. This is again for speed, but it is a pain. So this has now got us the correct destination, and the destination is stored in DE. Now we want to do a fill of the clouds. The clouds are 16 pixels tall, so we need to set that in B. We've got HL pointing to the memory address of the screen, DE pointing to the sprite data, and now we've got 16 lines, so this command or this command will fill those 16 lines. Now we want to do an area of blank space. Well, that's very straightforward. We just use a different program for that. Background solid fill will do that. It fills with the pattern DE, which is just zeros, and it does 32 lines in this case. Now we want another quad sprite. Again, this is now going to be the tiles for the buildings here. Now, rather than use get sprite mempos, we could use that to get the sprite memory position. We're going to take advantage of the fact that we know that our last sprite was 8 bytes wide, 16 lines tall. So we multiply 8 by 16, add it to the memory address we got last time, which we've stored in DE, and now we have the correct address. That's just a little bit faster than doing get sprite mempos again. We do have to be quite careful with our byte aligning and things here though. So now we're drawing those as well. Now we're drawing the next blank area just here. And you can see we're doing a lot of calculations here because we need to work out how much of the screen we haven't filled in. So this is just a subtraction of the screen height, less all of the other objects. So this is the kind of filler in between, and it's just blank again. Now we're doing the bottom gradient. The bottom gradient in this level is only 32. That's of course this here. And so we're just using the gradient command again here with a different gradient definition. And then finally we're doing the bottom, which is the floor, and this is another 8 pixel tall bitmap, a tile map, sorry. And so it's 8 here in B, and we are using the quad sprite routine here. So this is how we are able to do all of these sections. Now once we've drawn all of the screen, the gradients will scroll automatically, but the tile maps won't. And the way I do the tile maps is I actually bit shift the data in the tile map data after the background has been drawn. So what we need to do again is get back the memory address of the first tile. We need to set HL to 7. And we have to move to the far right hand side of the tile map because this is where we start. Then again we need a bit mask for the ticks. We're scrolling the clouds, so these move fairly slowly. So again we've got that slow moving mask here. And then we call the bit shifter, and this will actually handle the scrolling of the data. We need the correct number of lines here, and the number of bytes. It's always 8, to be honest. The code I thought originally when I wrote it might be used for other purposes, but it isn't. It's always 8 bytes wide. So we're doing the bit shift of the slow moving clouds, the mid moving buildings, and then the fast moving floor here. And you can see here these masks are different, everything else is the same. Now when we've bit shift an object, it automatically increments along, so there's no recalculation of the address for the second tile, but there is an inc h for the address of the third tile. There's an important reason for this. The tiles are all byte aligned along a 256 byte origin, and the problem is that the bit shifter, while it will increment the L register, it will not increment the H register. Now this tile is 16 times 8, which makes 128 bytes, and this one is 128 bytes. So we've now done 256 bytes. So L has completely cycled round back to 0, but H isn't auto incremented. So I've had to manually increment it here to point to the third bitmap, which is the floor here. So that's why we have to do that. It is a bit clunky doing this, and it was a real pain when I did episode 2 programming all of the data for the levels, but while it's a pain and it maybe takes a few hours or a day or two to get working right, it's pretty fast because it's like native code. There's no logic to it. It's not some kind of software defined thing. It's very fast. So although it's a pain to get set up, once you've got it set up, it's there forever kind of thing. And generally speaking, what I did with the levels in Chibiakumas is I took a previous level, made a few tweaks to it, just changed a few of the bitmaps around, so they all look different. But generally speaking, it wasn't like I was rewriting all the code from scratch. I was just tweaking the most similar level to what I wanted to end up with until it looked like what I wanted, and change the colors and things. So it wasn't as bad as it could have been. But anyway, that's what I've done. I'm sure there's other ways you could have done it that were better, but this was the best way I could come up with, and it managed to get the game reasonably fast. So I hope you've enjoyed this. Next time we're going to have a look at the code that does the flood fills and the tile maps, and we're going to see how we use the stack abuse to manage to get that filled really quickly. Thanks for watching today anyway, and goodbye.